So what I've got here is a description of the Square Kilometer Array Telescope project as it is now organized, and a little bit about the technical issues associated with it. So it would help me to know if there are a number of people in the room who already know about this. Okay. So this is a truly extreme scale computing project. And it is some of the comment I made about data streaming yesterday in the panel is directly related to what I've learned over the last few months, learning about this project and becoming involved. So here's what I want to talk about. Some of these slides I'm going to just show you and skip right over. If you get the slide deck and you're interested in this project, they'll be useful to you. It's a Square Kilometer Array Telescope is a very large radio telescope that, if everything works out, will be in operation by 2019, 2020. Right? It will be in 2 countries, 2/3 of it in South Africa and 1/3 of it in Australia. And the reason for those countries being chosen is that the telescope is going to be built in relatively radio silent areas of those countries, and the southern hemisphere has a better view of the universe than the northern hemisphere. There are 3 phases in the project. The first official phase started on the 1st of December 2013. However, the radio astronomy community has been working on this since 1990. There's a lot of background work gone into this. And we've just started on 3 years of design and engineering of the complete telescope. And it's really more appropriate to think of this as an observatory than a telescope. The procurement will not start until 2017, and the actual construction of at least the data processing part of this will not be start until 2018. Some of the infrastructure in terms of roads, power, fiber optic lines, etc. is underway, has started, and there are 2 precursor projects, one in Australia and one in South Africa. The Australian precursor project has just started accepting signals and processing them, and the South African one will start in 2016. It's right now in construction. Much of what I've got here you can find on the website for this, which surprisingly is skatelescope.org. Easy to remember if you're interested. So the first phase, which is called SKA1, it is not called SKA, right? SKA. Right? The first phase constructs some number of antennae in both continents. I'll get to that later on. And I'll also show you the dollars involved, like the euro involved. And then the next phase, SKA2, extends from the base, so that by the time about 2024 this is finished, there'll be something in the region of 5,000 antennae, right? Some of them actually consisting of tens of thousands of smaller antennae. And in Australia, it will be spread from Western Australia into New Zealand. And in South Africa, it will be spread from South Africa up to Nigeria. No, I think it's Ghana. So this is a fairly large project. The budget at the moment for the first 3 years, which is the only part that's funded, comes from the countries that are involved in this, and I'll show you what they are. And it's about 90 million euro. I'm sorry, there's an error there. And in terms of design and engineering, and set for the actual construction of SKA1 is 650 million. And now I'm going to transition, that's just a very brief summary. Now I'm going to transition and look at some of the computing involved here. That's a cartoon of the kind of system architecture that the project is thinking about. So the data comes in from the sensors, which are either dishes or arrays of dipoles. And over fiber lines, it's brought into a switch and then a correlator. And the correlator has basically two functions. One is to allow the data to be recognized from the noise. These are very faint signals. Perhaps I should digress a second to something novel here. What's the purpose of this? The purpose of this project is to discover what happened after the Big Bang during a period of time that there was no ionization. Okay? And then hydrogen ionized, and then elements started to form, and then as elements started to form, things started to get mass. And as they got mass, they aggregated into stars and other gases, and then something solid, and then the solid started to aggregate, and what we now have are some number of galaxies, right? And in those galaxies, there are some objects that are becoming too close together, or very close together, and spinning with pulsars. And my knowledge of astronomy, somebody will tell me I'm wrong, from pulsars we get black holes. And what happens in the black hole? Right? I don't think anybody knows. Right? And so this is a project with some pretty grand vision. Sorry. Okay. I'm sorry. And so I got interested in this because this is about as interesting a project as I could imagine being involved in. Right? So back to the computing. So the correlation is to find the signals in one and actually capture them in the correlator or computer that's doing correlation in such a way that they can then be forwarded on to the science data processor, which turns what has been captured into data in a form that can be used by astronomers to create images and get other information. The other thing the correlator allows is to form what are called beams out of the signals, and the beam can be used to capture wide information from signals in the universe, whereas the correlation is usually used for a point that's being observed. The beams are used for surveying the universe, looking for things that haven't been found yet. So after the correlator, there is another switch, and then it goes into the science processor where the data is converted into what are known as visibilities. And from visibilities, astronomers can start to learn something. It's archived, and then the data will be distributed worldwide. Exactly how hasn't been defined yet, to astronomers all over the world. In the lower half of this slide are some of the numbers involved with just the very first part. And these numbers, there's a wide variation of estimates available in this program. There is something in the order of 300 astronomers involved in this program. And of course, there's more than one opinion amongst them. So the South Africans have estimated these numbers. So by SKA1, there'll be about 50 terabits per second entering the correlator. The DOE. The data out of the correlator about 20 terabits a second, right? Into storage at something around 300 gigabits a second, right? And the computing load at least 30 petaFLOPS, which is not a large computing load actually today. 300 gigabits. Yes. Yeah. But maybe not for data that's moving. It's relatively static as it is in other. So how is this project? That's as much as I'm going to show you on technical stuff until we get to the end, because I think if you're interested in this, how it's organized and how it's going to come about is of interest, and there is plenty of opportunity to participate if you have strong interest. So it's 10 countries at the moment, not including the United States. At question time, I'll explain why. There's a board of directors representing those 10 countries. There's a director general and an office. And the director general and the office are located at Jodrell Bank Telescope, which is a few miles south of Manchester. The reason it's there is that the Jodrell Bank radio telescope was the very first radio telescope was at Jodrell Bank. And it was created out of disused radar equipment from the Second World War by a man by the name of Bernard Lovell, who lived very close to Jodrell Bank. And then the design work is being done by what are called work package consortia that were sorted out in the last 12 months. And in many ways, quite like an open source community, the work package consortia got created amongst the 300 or so people interested by a very informal peer review of each other and selection of who they thought could lead certain parts of it. And they came together. And you'll see all the institutions involved in these work. So the siting decision was made in 2012. The current corporate organization is a non-profit in the UK. I've mentioned what the budgets are for the moment. Each consortium has to come up with, by the end of 2016, a set of documents that they deliver to the project office to allow the project office or its successor to do the actual procurement of the pieces. Board members from most countries are made up with somebody who's collected politically and somebody who's a leading astronomer. The design is being done in different levels of organization in the consortia and is quite open, but the project office has engineers or astronomers assigned to every consortium who have the last say in what is being designed. For those of you who are interested in some parts of these, I thought I would put at least in the presentation the names and the locations of the leaders of each consortium. So if you get this slide deck and you're interested, you can contact those people. As I mentioned, the US is not involved in the consortia, but if you peel back the layers here, where is the computing going to come from? Where is the networking going to come from? The dishes that are being tested at the moment, considerable parts of them are being manufactured in the US, right? And the US decision not to be involved was a short-term, budget-driven decision in the National Science Foundation. And from the point of view of US academia and industry, I don't believe that we should allow it to be a long-term decision. And certainly from an economic benefit point of view, US companies are at the heart of this. And I'll say a little bit more about that towards the end. In the following slides, I've got the lists of all of the consortium members, again, for the same reason, that if you are interested in this slide deck, you can find out how to contact the people. Those of you that have run large projects, you can imagine the herding of cats that has to go on here, right? And in fact, in each one of these consortia, because I've been involved in some of the meetings, you can start to pick out who the really influential people are, right? And it really is an individual basis. That's what I've observed so far. I mean, in this one, I would say the Canadians and the South Africans and the Australians are really the leaders. Here's what a dish looks like. Can you all see there's a person standing underneath this? Right? That's actually an artist's impression, but the meerkat dishes are not much smaller than that. And that person, I recognize that person. He is the technical leader of the South African project. On the website, you can see pictures of how far the South Africans are along and how far the Australians are along. But eventually, there will be, I think, 2,500 of these things spread throughout Africa. Sorry? Yes. I don't think Alma is offset. Different dish design. They are offset. Here's some information about the construction of one of the candidate dishes, and this is where, if you look very closely, you'll see, oh, this is being manufactured in the U.S. So that's one of the bases on which I say that the U.S. ought to be involved in this project from a economic point of view. The low-frequency aperture arrays, this is the consortium for this, and I don't know this one well enough to know who the leaders are. But I think the University of Cambridge, Cavendish Lab, I've seen a prototype of one of these in the Cavendish Lab in Cambridge, and I think they may very well turn out to be very influential. Here's a mid-frequency consortium, and some of this very same people. The top picture is what the dipole artist's impression looked like, and the one I've seen in Cambridge, there are no flat surfaces, they're all rods, and very cheap to manufacture. And then they are deployed in the desert in two different ways. One in the top form, and then the form in the middle is what the low-frequency aperture array in the Netherlands looks like. You go and look on the very far left side, it looks like that. Okay? And here's the idea in the lower picture of being formed in this area. Yes. Signal and data transport. Traditionally, the astronomers have designed their own protocols, their own way of connecting dishes, the antennae to computers, and there is a significant struggle going on in this consortium between adopting industry standards or rolling their own thing. And that discussion will go on for some period of time. It's run out of the University of Manchester, which is being the locus of the let's do it our way, let's not use the industry standard way of doing things in the past. So we'll see what happens here. There's a diagram of the network from a conceptual point of view on the top, and then from a technology point of view at the bottom. At this stage, I won't say more about it, but if you are interested, I'll talk a little bit more about it offline. Central signal processor. That's very interesting because, again, the astronomy community over the past has rolled their own. The biggest correlator at the moment is in the US. It's in the very large array in Socorro, New Mexico. And that took 10 years to design and build. Okay? And so there's a tussle going on about this consortium as to whether to roll our own everything of our own design to let's use an Intel processor and write some software. Okay? And there are many stages of chips and software organization between those two, and that tussle will also go on for several years. The leader of this, the technical leader of this, is a guy by the name of Bruce Carlson in Canada, and he was the designer of the very large array correlator, it's called WIDAR. So, and then there are others, most strongly in Australia and New Zealand, as well as in Oxford, who have different views about how this should be done. Here's the list of options they're considering, and a little bit of analysis from the Consortium about the pros and cons of each approach. This is, from a software perspective, a little bit like what the correlator looks like. And what you'll see here is that it's streaming, and there are multiple streams at different frequencies being processed simultaneously. So, and at the end of the correlation part, it's written to storage and also transmitted at the same time. So here's the science data processor consortium. Again, I'll just make a comment that organizing this number of different people to get together to work on a task like designing the science data processor is just a major, major sociological endeavor. Okay? The leader is a guy by the name of Paul Alexander at Cambridge, and he had a pretty tough task in his hand to figure out how to pull these people together to do the design work. One of the things that's he's doing to help this is to create an open architecture lab in Cambridge, and he does have funding to put hardware into that lab and prototype it. His comment in public about the theme of this consortium is that they're going to buy their hardware at the last possible minute, and it will be commodity. So that I think, from my perspective, is very encouraging. I guess I have also left out the fact that this observatory, two observatories, are intended to operate for 50 years from the 2020s. Okay? So I don't think in the HPC community we design things that we thought were going to last for 50 years. So that also is an interesting perspective on how to do this. I said a little bit here about what the computing tasks are for the science data processor, and an interesting aspect of this and in the correlator is the appearance of buffers in the stream, which we've just seen that appear in the HPC community for the DOE labs, that getting data out of the machine, they need what they call burst buffers in the DOE to do that. And at the same time, that is showing up in the thoughts of how to design this in SKA. So this is, I'm very interested in the number of cores that are available for Blue Gene Q. There's actually a Blue Gene P being used in the Pathfinder in the Netherlands for some of this work. And I don't know how many cores they have in that Blue Gene P. There's thousands of different streams going through this machine without stopping simultaneously. And unlike HPC, the radio astronomy community is relatively comfortable throwing away small amounts of data because there's another set of data arriving and reduced in a fraction of a second. Right? So reliability from the point of view of processing every bit is not a requirement, but staying operating is. Right? So that's a trade-off to think. The design approach for this is a series of vertical and then horizontal moves down the design process, which I'm looking forward to experiencing this as to how this works out, but this is the theory about how they're going to do it. It's a little bit more detail in this diagram for just the science data processor. Okay? And the intention is that they'll be able to choose the best chipsets regardless of the instruction set architecture but they create software that's homogeneous across them. A similar kind of diagram of the correlator in terms of multiple beams being processed, multiple streams being processed simultaneously. There are some more numbers associated with this. These are estimates from Cambridge, and about the numbers of, for example, the Aperture arrays are producing, in his opinion, about 1.5 bytes a second, and when the long baseline, which is distance between antennae and the baseline of the stream that you're dealing with, there's quite a lot of fairly high data rate. So here's Paul's estimate of sizing. A little bit different from the numbers we've seen before. The beamforming and the survey of the universe, much higher data rates out of the correlator, and then a computing load that's about the same, and then a petabyte-sized buffer for putting it in before it goes into the archive. But just the survey on the low frequency apertures, which are in Australia, and the dishes, which is SK1 mid, are in South Africa, and they have a very different data rate. So there's actually two computing systems to be built here, one in Australia and one in South Africa. Here's the telescope manager, interestingly being led by India. The Indians actually have quite an advanced radio telescope. So this is probably, from a software perspective, may well be one of the more interesting parts of this, is to create software that can manage the observatory in real time, all the different parts of it, simultaneously. That's what the task of this consortium is. Somewhat different from system managers that we do in HPC, a little bit more extensive. The infrastructure is being done in both countries separately, and so is the survey verification. So I've mentioned the timing before. Now you've seen all the consortia, I think you get a different perspective of what the task is and why it's going to take at least 3 years, right, to get everybody together on this. SKA2, there's very little information about. It's mostly taking the learning out of SKA1 and then scaling it up by a factor of 10. I'm trying to build 10% in SKA1 and 90% in SKA2. So now I want to mention a little bit about the US. The US astronomy community was really very upset that the US decided to back out in 2010. And as a result, there were a number of astronomers who wanted to continue, at least to be working in the field at this kind of scale. And so Henry Brandt, many of you may know him from IBM, asked that a consortium be formed to allow the US astronomy community and the US computing industry primarily to continue to work at this kind of scale. And so we formed a consortium called RARIC. It is based in the US, but it's not exclusively in the US. You can see it's a 501c3 as a foundation as opposed to a C6, which is an industry association. And I didn't bring all the details of this, but the consortium exists legally. It has bylaws, it has a board of directors, and its founding documents are all in review by the members at the moment. I believe by March that will be complete. We're up and running, okay? And we have a software correlation group and a data management group, that are at work, just started, and the Foundational Technologies Group, Alan and I just kind of got the focus of the Foundational Technologies Group is to be able to describe as industry people what sort of technology we think can be used by astronomers and engineers to design in 2016 and 17 for something that's going to be built in 18 and put into operation in 19. A normal NDA with a company like the one I work for would not address that time frame at all. Right? And so, and it turns out, with a little bit of analysis, competitors like IBM and Cray are actually dealing with the same supply chain, the same suppliers for building what they're doing. And so if we work with our suppliers, we can get a sense of what we're going to have available to us in the time frame. That's what this is for. And then we're very open to other working groups, and I'd encourage any of you who are interested in participating in this to contact me. Okay? I'm currently the acting executive director of this thing. Thank you, Brian. I turned into a zero. I think I'm almost done. So I've got some slides here of what the SKA team think are the issues in building the kind of computing capability for the science processing. The correlation people have not done something like this. And I'm not going to go through these slides, but from a computing perspective, and maybe from a data handling perspective, these are not quite as extreme as they used to seem a couple of years ago. And then almost certainly actually the bigger task is the software, and at all levels, from the operating system through to the application. And work has been going on with algorithms, and but I don't believe there's been any compilers and libraries developed so far. I'm done.